Yes, so we talked about how a power series basically will have three different scenarios for its convergence. A power series will converge to a real number or converge with a function, perhaps only at one point, or perhaps for all values of x, or perhaps like the one we just looked at for a limited domain. In this case, it was -1 to 1, but it could be -1/2 to 1/2. It could be 3 to 1, or it could be -5 to 12, or it could be any combination of numbers there. So basically, if you wanted to boil it down, a series is going to converge at one point, all points, or just a limited domain. Those are the three categories. We're going to call this number r. We're going to call it the radius of convergence. So let me just sketch this out based on that graph real quick. I wasn't planning on doing this, but maybe this will be a good connection for you. So if you think about the blue graph and the red graph you just saw, here was the blue graph, right? And then the red graph came in and it did something like that. Make sense? So we noticed that this over here was at about -1, and this right here was at about 1. So here's what we would say graphically. I want to bring this in to help you understand what's going on. This radius of convergence would be, well, maybe I should ask you. What would you guess the radius of convergence would be for the one we just looked at on the calculator? Think about the word radius. Radius is the distance from the center to the outer edge. So say again? 1, yes. So this full distance from there to there, obviously we understand that that's 2, but the centering point is 1. Excuse me, the centering point is 0, so the radius is 1. Does that make sense? So I would say the interval of convergence for this is -1 to 1. This would be the interval of convergence. If you were asked for that, the radius of convergence would be 1. So if you're centered at 0 and the radius is 1, you're going to go from -1 to 1. If you're centered at 9 and the radius of convergence, say, is 2, what would be your interval? 7 to 11, right? So if 9's the center, you'd go +2, -2 to get your full interval of convergence. Okay, cool. So then, anyway, so you can establish that radius and interval of convergence, and we'll be analyzing these things using the ratio test. So this is a good review of the ratio test. The series converges absolutely if the limit of the ratio is less than 1. You're going to get a diverging series if the limit of the ratio is bigger than 1. And if you get exactly 1, the ratio test is inconclusive. So I want to focus on what we're actually going to be using here. We are only going to be focusing on this piece right here. The reason why we're only going to be focusing on that piece right there is because we're looking for intervals of convergence. Looking for convergence here. So we're not looking for an interval of divergence. We're looking for an interval of convergence. So we're only going to be focusing on that first piece of this ratio test. Okay. All right, so we're going to do a couple of examples looking at the radius of convergence. And so I thought I'd maybe do one of these with you guys and leave one and or the other up to you to try to work through and see how this goes. So here's what you would do. Looking at this, I've got the series. It's an nth term. It is an alternating series, right? You can see that alternating element right there. But if you remember the ratio test, it does the limit of the absolute value of the ratio that we're working with. And so that alternating piece is going to be taken out. So here's how I'd set this one up. I'd write out limit as n goes to infinity. And then if you remember, the ratio test is essentially the n plus 1th term divided by the nth term. So what I'm going to write is x. Are you guys okay if I distribute the 2 and get x to the 2n plus 2? And then down here it would be 2n plus 2 factorial. Is that too much arithmetic skipping? Tell me if it is. I'm basically replacing all the n's with n plus 1s. Sorry. It's okay. I didn't know if I could get away with that or not, and I can't, and that's okay. So x to the 2, I'm replacing all the n's with n plus 1s. And same thing down here. So do you see how I could then distribute the 2 and get 2n plus 2? Okay. And then we're going to multiply that times the reciprocal of the nth term. So that would be 2n factorial over x to the 2n. And then maybe the most important thing here is we want to write this. That limit of that ratio is less than 1. Okay, because we're looking for convergence. So I'm going to say, whatever that limit ends up being, it's less than 1. Pretty scary looking thing, but if you remember from the ratio test, we can break these down pretty quick and simplify them down to something fairly simple, fairly rapidly. So,
do you know it's less than 1, or are you just setting it up to see it?
I'm not setting it up to see if it is less than 1. I'm setting it up to see, this would be a good thing to say right now. What I'm doing is I'm setting this up to find out the x values for which this is less than 1. Because I'm looking for an interval of convergence, and like we did with the one on the calculator, we found out, at least kind of casually speaking, that the interval of convergence was from -1 is less than x, which is less than 1, right? And so I'm basically trying to find the same sort of thing for this. Like, for what x values is that true? Is that good? Because if I can figure out what x values make this true, then I'll know my interval of convergence, I'll know my radius of convergence, so on and so forth. Okay. All right, so then if I do that simplifying stuff, x to the 2n plus 2 over 2n plus 2 factorial, and then up here it's still 2n factorial. Down here it's x to the 2n. We're still looking for where this is less than 1. And this is where I can start doing some algebra and simplify things. So if I'm dividing x's like this, if I'm dividing bases, what do I do with my exponents? Subtract. So aren't the 2n's just going to subtract right on out of there? Okay. So that's going to give me a limit as n goes towards infinity, and it's going to be x squared. That's kind of good. And then I look at my factorials. So see if you can picture this. I can write this out if you want. Wouldn't 2n plus 2 factorial essentially be 2n plus 2 times 2n plus 1 times 2n plus 0, or just 2n? Okay, so what I'm going to do is I'm going to think of, I'll write this in a different color just so we can kind of see it. I'm going to think of this 2n plus 2 factorial as 2n plus 2 times 2n plus 1 times 2n factorial. Make sense? So what I can then do, of course, is cancel the 2n factorial with that 2n factorial, leaving me with 2n plus 2 times 2n plus 1 down there. Okay, so this is where this one is kind of interesting. We're going to be done with it like right now. As you apply that limit, as n goes to infinity of that expression right there, realize that the n going towards infinity does not directly affect the x at all, right? Doesn't it only affect the n's? So if you think about what's going to happen here is both of those two n's down in the denominator, as they get super huge, really huge, what does that mean for the fraction? Heading towards 0. Specifically heading towards 0. It doesn't really matter what x is. X can be the biggest number that you or I could think of. And it doesn't really matter. If the denominator is getting huge like this, we are heading towards 0. So this brings us to a very curious conclusion. 0 is less than 1. So you're kind of like, yeah, 0, sure. Yep, last time I checked, less than 1. So here's what this really means. There was no x left over at all, right? There was no x left over at all. We're going to contrast this here in a second. On one that we'll do here in just a few minutes, we're going to see that there is an x left over. There is. So here, what this is basically saying is this. It doesn't matter what x is. This will always be true. It doesn't matter what x is. So if x doesn't matter at all, x could be any number you could possibly dream up. What's the radius of convergence? Infinity. Right? So think about what that means. Like literally, if we look at this and we're like, I guess that means that x doesn't matter. what could I plug in? Well, you might think of a really big number, like, you know what, I thought of a bigger one. And then Darian's like, well, I thought of a bigger one than you. Can't we just keep one up each other forever and ever and ever? Aren't we talking about infinity? And so I would say, based on this analysis, that the radius is infinity. And it doesn't ask for this. It did just ask for the radius. But if it also asked for an interval of convergence, I could say this. I could say that the interval is from, I'll just do this. Interval is from negative infinity to infinity. Let's talk about a little bit more why this is. Is there any chance that anyone recognized that? I'm asking, it's a little bit of a stretch. I'm just kind of curious. I wouldn't expect you to recognize this yet, but soon I would. What do you see going on up there? There's a very specific pattern. A couple of them. What kind of series is it? Alternating. That's important. What else? What other patterns do you notice? Think about the two ends. What does 2n guarantee? Even, right?
Yeah.
If your inputs are 0, 1, 2, 3, 4, 5, dot, 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 if it's 2n, doesn't the 2n guarantee that the output is even? So what kind of a function have we looked at that's had factorials in the denominator, and it's alternating, and everything's even? We're not there yet, are we?
No.
That's okay.
Sorry.
No, it's okay. It's okay. I told you. I told you this was a stretch.
Okay.
I thought maybe someone will pull a Sean and be like factorial, but no, it's okay.
Come on, Sean, got this.
This is cosine.
What the?
This is cosine. I'm sorry, I didn't hear you. Did you say it really quiet?
Yeah.
Yeah, this is actually cosine. This is the power series for cosine of x. Okay, so don't worry about memorizing it. There's a list coming up of things you got to have memorized for later on. This is one of them. Okay, so doesn't this go with the graph that I just showed you? Yes, does that make sense? The graph I just showed you, like at the very start of the video. Remember how the interval convergence went from really tiny to this, to this, to this, to this, to this? So doesn't it make sense that the radius of convergence would be infinity for this power series? Okay. All right, so we're going to do some skipping around here. So let's jump a little bit. Let me remind myself where I want to go. Oh, I'm sorry, McKenna, go ahead.
So since like x doesn't matter and the limit equals 0, the radius is infinity?
Since x doesn't matter,
It's like,
the radius is infinity.
okay.
Mhm. Yep. Okay, so we're going to look at a slightly contrasting situation to this. I think, do I want to do that one? Do I want to do that one? I would like to do this one. Let's do the one we just were examining on the calculator. So jump ahead a little bit to number 6. We'll do some jumping around here because I want to just you guys to get some comparing and contrasting so you don't think that everything is always this or everything is never that or whatever. I want you to try to get as diverse of a picture as you can. Okay, so this is the one we were working on the calculator. And on the calculator seemed to be indicating that the interval of convergence was from -1 to 1. Okay, and we're going to do part of this, and we'll probably come back around to this a little bit later, but I want to at least kind of set this up to help you understand where that came from. So we're going to use the ratio test again. So here's what I would do. I would set this up and say the limit as n goes towards infinity, and it's going to be the n plus 1th term divided by the nth term. So this is going to be x to the n plus 1. And I'm not going to do the whole copy dot flop here because the terms are really, really simple, right? So it's going to be x to the n plus 1 over x to the n. That's supposed to be less than 1. So this is going to be a pretty stark contrast to the one we just did. So that's your ratio. You set it up. You're like, all right, what do I do? We're going to try to simplify stuff, right? And so like before, if you've got bases that are x's and you're dividing them and you want to simplify it, what do you do with your exponents? Right, so the n subtract out, n plus 1 minus n is just x to the 1. So it's going to be limit as n goes to infinity. And in here we've got x to the first, or just x. So I told you this was a significantly contrasting example, because in the previous example, when we applied the limit as n goes to infinity, it made the whole result end up going to 0, right? Well, check this out. Now the limit doesn't even matter, does it? There are no n's left for the limit to do anything to. So the limit of the absolute value of x as n goes to infinity is just that, right? Because the limit as n goes to infinity doesn't even apply to this, because there's no n's. So then this is maybe going to take you all the way back to your Algebra 1 days. Do you guys remember how to solve these absolute value inequalities? Ah, trip down memory lane. This will be lovely. You remember? There's a positive and negative involved, I agree. So there's two cases, right? Because we're talking about different sides of the number line. So the first case is this. This is kind of the positive case for absolute value. We would simply say x is less than 1. And then the other case, of course, would be, what about negative 1, right? Because that's the same distance from 0. So with that one, I'm going to put an x and I'm going to put a negative 1, but this time the inequality flips around. So it's this case right here where x is less than 1 and x is greater than negative 1. So you might have commonly seen this written like this. Negative 1 is less than x is less than 1. And now you look and you compare that to what we saw on the graph and what we think about with the geometric series, and maybe this makes sense. Are you connecting it? There's a lot of connections to be made here. I don't want you to compartmentalize and be like, oh, this is different. It's not. It's the same. It's just looking at it from a different angle. So the thing I want to leave you with here, we're going to jump back and forth a little bit. Like, oh, I'm sorry, go ahead.
This way, does that mean the radius of convergence is 1?
So yeah, so this, great point. Let's bring that up. So the interval I've given, right? If this did ask for a radius, you'd say, well, this pretty clearly is centered at 0, right? And it even says centered at 0. And we can see the plus minus 1 action, so we'd say the radius is 1. Agreed.
Okay.
So this is the interval of convergence up here. This is the radius of convergence. Okay. So the thing I want to leave you with, and we'll come back around to this a little bit, probably today, definitely next time we have class, is these two inequalities right here. I left them open. And of course, when the expressions on the left and the right are infinities, like we did on the first one, then you got to leave them open, right? You can't close it on infinity. Be like, hey, counted to infinity, got there. Can't do that, right? But then you might ask the question, how do we know that those intervals are left open on the left endpoint of negative 1 and the right endpoint of positive 1? How do we know that maybe one of them's not closed, or maybe they're both closed, or how do we know they are both open? Because this is a geometric series, you could probably answer it pretty casually just by saying, hey, if the common ratio is 1, it's going to fail the nth term test, right? But other scenarios, it's going to be a little more complicated to deal with, and that'll be one of the things we'll deal with the endpoint analysis as well, okay? So is that a good comparison? Do you see the difference between the two? We'll do some more comparisons like this. Okay, fair enough. Let's then go back to number 2. Number 2 is right there. Okay, so I think you'll find this one to be similar-ish, kind of, sort of, a little bit like number 1. So I thought maybe this would be a good one for you guys to start to try on your own. So if you guys would, try to find the radius of convergence for that one. So that's your setup right there with the ratio test. Your next step would then be to, well, like we were talking about, literally reduce some fractions. So if I look at this and this, I'm going to subtract my exponents. And so that's going to give me just x to the first up there on the top. And then when I look at the factorials here and here, did you guys just leave that as n plus 1 in the denominator? Because the n factorials beyond that would cancel out. So really similar to number 1. And this is all still supposed to be less than 1. Can you see how this turns into something just like number 1? Right? Because as you apply this limit, it really doesn't matter what x is because the denominator is getting gigantic And so the overall value of the fraction is heading towards 0. So again, you'd get this 0 is less than 1 thing. And like we did with number 1, but different than number 6, the x has essentially been reduced to 0, right? There's no x. And so that means the radius of convergence does not depend on x at all. Therefore, the radius of convergence is infinite. So if you had r is equal to infinity for your radius of convergence, you're definitely right. If you had to give an interval of convergence, wouldn't it be the exact same as number 1? It would be negative infinity to infinity if you did that with the parentheses, the interval notation. Yeah.
Do you need to cite anything you're using? I know in all the other ones you had to be alternating series test or something.
Yeah, so we're just using the ratio test every time. So every time when we're looking for these intervals or radii of convergence, we'll always use the ratio test. So you don't have to name anything, just basically set it up and start evaluating and simplifying and getting it down to hopefully a good answer. So Sean, you want to say it? What is it? It's e to the x. This is right here. This is the series for e to the x. Maybe you remember that. Maybe you don't. It's fine. He said it really early, and I told him to be quiet. And it's okay. It's okay. Okay. Be nice to Sean.
I know I am. Sean's the best.
He's the best. Man, Sean. Okay, I will say he notices stuff pretty good.
It's pretty brilliant.
So, we okay with 1 and 2? Sure. Let's just finish up number 3 really quick. Again, this looks really scary, but I think you'll find number 3 to operate much the same as number 1. Okay, so let's think of this as kind of a capper on these radii of convergence. Then we'll do a couple of full intervals of convergence, and I'm sure that'll just about be our time. So please attempt number 3.
So do you just ignore the alternating element?
Did you guys get this for kind of your initial ratio?
Yeah.
After you distributed and maybe added the 1 to the 2 and did all that? So hopefully pretty quickly you were able to reduce this down and see x squared over 2n plus 3, 2n plus 2, less than 1. And again, really similar to number 1, as you apply the limit, the numerator is held as just x squared, the denominator gets gigantic, and you end up with a 0 over there. So 0 is less than 1. Therefore, again, your radius is infinite. And if you had to write an interval, you would say negative infinity to infinity. Okay? So final chance here to someone best Sean on this. Any guesses as to what that power series represents? Sine is right. Great job. Sine of x is what that power series represents. So it's alternating, right? So the Maclaurin series, the Maclaurin power series for sine is alternating. And did you notice how 2n plus 1 creates all odds? 2n plus 1 will always result in an odd, giving you sine. Okay, so I want to go back to kind of working with you guys and demonstrating a little bit here with number 4. Yeah. Yeah, let's do number 4. Okay, so this brings up the question that I asked you about when we skipped ahead to number 6. So the ratio test is going to supply you with the radius of convergence. And the first 3 cases we looked at there was infinity. When we looked at number 6, it was 1. And so we're going to look at some other ones where this radius of convergence is going to move around a little bit. So number 4, here's what we're going to do. We're going to do this when we're looking for an interval of convergence. We're going to do this just like we did before and find the radius first. So we're going to say limit as n goes towards infinity. And it's going to be x to the n plus 1 over n plus 1 times n over x to the n is less than 1. So just kind of that standard ratio test setup. And as we try to simplify this down a little bit, we're going to see that it turns into the limit as n goes towards infinity, and it's going to be x, I'm going to write it like this, x times n over n plus 1. Right, because the n over n plus 1, nothing's going to cancel but the n's subtracted off those exponents of the x's. So now, as you apply the limit as n goes to infinity, it's really only going to apply here. And so using maybe the pre-calc trick or like a real quick mental L'Hopital's rule, what's going to happen with just that part?
Just becomes 1.
Just goes to 1, right? Because the degrees are equal, therefore you just use the ratio of the lead coefficient, so it's like 1n over 1n plus 1. And so I would say this would result in absolute value of x times 1, if you want to write that, you don't have to, is less than 1. Does that seem logical? Is that good? Good reasoning? Okay. So isn't this really similar to the geometric one that we looked at? Like we got to this same step. So I would say at this point right here, if I wanted to, like if all I had to give was the radius, I could say, therefore the radius is 1, right? The absolute value of x is 1. We're centered at 0. And how do I know I'm centered at 0, by the way? Any ideas? Does that help? I could pose the question differently. If I was centered at anything other than 0,
And that would be x minus.
it'd be x minus whatever, x plus whatever. The purple highlighted x up there, do you see it? If I was centered at anything other than 1, it would be like x plus 2, parentheses to the n, or x minus 5, parentheses to the n. So I know I'm centered at 0. Make sense? And I can see that the absolute value of x is less than 1. My radius is 1. So I could then, since it did ask for the interval, I could then take this one more step further. Are you guys okay with this? If I took this and said negative 1 is less than x, which is less than 1? If you're not comfortable with that, we could use the little absolute value inequality thing and say this splits up into this and this. X is less than 1, or x is less than negative 1. Are you guys having a hard time seeing that? Just be honest. Are you seeing it? If you're not seeing it, okay, I can show you a picture of something that maybe would help. Y'all okay? Okay. So when I look at this right here, I'll erase this in a second. I think of a number line. Remember, it's sort of a lame definition. It's not the greatest definition in the world, but remember the old definition of absolute value is the distance something is from 0 on the number line. So here's 0. And if I'm saying that the absolute value of x, some unknown number, is less than 1, what are the two numbers that are 1 away from 0?
1.
Yep, so there's 1, there's negative 1. Now how do I decide whether I want this or that? Well, I decide that based on the inequality. So this is basically saying, I'll highlight it, this is the distance from 0. So we want the distance from 0 to be less than 1. So which numbers are at a distance less than 1 from 0?
All numbers up to 1.
Numbers like 1/2, negative 2/3. So in other words, all these numbers right here. And so based on that graph, I think I would comfortably be able to say this right here and then make that translation over to just the single statement. Does that help?
Yeah.
Okay. Okay, so let me get rid of that real quick. So then finally, so this is no different than what we've done so far. Finally, we come down to this last piece of information, and that is, how do I know for sure that the endpoints are open, or maybe both endpoints are closed on this interval, or maybe it's a mix or something? How do I analyze this? Okay, so here's how I do this. I'm looking at this right here, and I would say that this that I just put in that purple box, that's kind of like my provisional. I'm not quite there yet. Interval of convergence, I got to decide about the endpoints. I'm going to go over here and do some analysis and decide, is that correct, or do I need to make a few changes? Okay, so here's how I'm going to do that. I'm going to say for the left endpoint, so for x equals negative 1. So I'm going to test the left endpoint, figure some stuff out, and then after that I'll test out the right endpoint, figure some things out, and then I should be able to present a final answer. So for x equals negative 1, my series would be this. Sigma from 1 towards infinity, And I can just replace the x there with negative 1. So it's going to be negative 1 to the n over n. And this is a moment when all that work you did with series, convergence, divergence just might pay off. So when you look at this, when you look at that right there, the hope is that you did enough work, or you will be doing enough work with series to look at that and say, oh, I know what that is. Does anybody know what that is?
Harmonic.
It's an alternating harmonic. That's right. So here's what I can do. If I can identify that as an alternating harmonic, which that's exactly what it is. Nope, it actually converges.
That's what I meant. It was
Nope,
opposite.
alternating harmonics converge. Harmonics always diverge. Remember how the plus minus thing helps convergence? And the 1 over n, like it's like super close to converging. It's like almost there. And the plus minus pushes it over the edge, right? So you could also, if you wanted to, so here's what I'd do. I'd say converges, and I'm just going to put alt harmonic. So I'm just naming it. And if you can name it and say, hey, therefore I know it converges, that's really all you have to do. If you wanted to get all detailed and say, this is an alternating series and the terms decrease in absolute value towards 0, therefore by the alternating series test, the series converges, you're welcome to do that. Or you could just say, hey, it's an alternating harmonic, therefore converges, done. I think that one's easier. McKenna.
So that would be a conditionally converging?
It would, yep, that would be conditionally converging. Yeah, because if you take away the plus minus, we don't need to concern ourselves with that for this. But thinking about your quiz tomorrow, yes, that makes perfect sense. Okay, so there's my analysis on the left endpoint. The analysis on the right endpoint, that would be for when x equals positive 1. I'm going to say that is sigma from n equals 1 to infinity of now positive 1 to the n over n. Again, all your hard work with these series, and you're like, okay, what is that? And you would say, it's a harmonic. That's right, and harmonics always diverge. So I would say this diverges, and my reasoning would simply be to say it's a harmonic, and I know that all harmonics diverge. Okay, so then my final answer, I need to take those two pieces of information into account. On the left endpoint, I got convergence. And on the right endpoint, I got divergence. So my final answer would be this right here. Negative 1 is less than or equal to x, which is less than 1. So the reason why I put the or equal to on the left endpoint is because I got convergence at the left endpoint. The reason why I left it off of the right endpoint is because I got divergence on the right endpoint. So this right over here, I should probably get rid of the box that I put around that, because a box indicates that you're done. I put final answer over there, right? I'm indicating, hey, I've done my analysis on the endpoints, and now that's it. I've revised my other answer. Okay, what do you think? So this is just like what we've been doing, except you got to do the endpoint analysis, which is depending on how good you are with these series that we've been working on. So hopefully we've done enough work. If we haven't, we still have time. Yeah. Okay. I'd like to do one more little experiment with this. I think that'll put us in a good spot. And there's, I think, a number 7. Yep, okay, we'll definitely save that for next time. Let's take a look at number 5. Number 5 should be good. We got about 6 minutes. That's borderline enough time. If it's not, that's okay. We can just pick it up next time. But do try. See what you... That's my start. See if we agree. Did you guys also notice something about the centering point on this one? What would you bet the centering point is? -1. Yeah, you're right. Nice work. Okay, I'll let you keep working. You guys get that after you simplified? Okay. you guys notice that the limit as n goes to infinity doesn't really matter here? It doesn't apply to x.
See, now I know what to do.
Can I help you guys with endpoints real quick?
Yes.
Did you guys get here? So what's the radius? 2. The radius is 2. The centering point is -1. So if you wanted to build this out and get a basic kind of an interval, what did you guys get? -3 to 1? Okay. So -3 to 1. And we don't know yet about what's going on with these endpoints. So here's what you could do. The endpoints I think are pretty tough. For x equals -3, it would be sigma of, it would be -1 to the n times, wouldn't it be -2 to the n when you do the -3 plus 1? All over 2 to the n. So if you think about how this would work out, or how this kind of has worked out, you could break this down. Let me just see if I can fit this in here. If you got -1 to the n and -2 to the n, do you guys realize that that is the exact same thing as -1 times -2 to the n? Because couldn't you just reapply the n to both bases? I'm just undoing what's called the power of a product. Still over 2 to the n. Well, what's -1 times -2? So this is 2 to the n over 2 to the n, which is, well, yes, and the common ratio is
1.
therefore diverges. Yeah. So you would say
I thought, like, dude, don't worry.
diverges because the common ratio has to be between -1 and 1, but not including the endpoints. So I just would say diverges GST R equals 1. So you're just making notes about this. And then the other one is a little different, right? So the other one you'd say for x equals 1, you get sigma, and you'd get -1 to the n, and then you get 1 plus 1, so you get 2 to the n over 2 to the n. So those cancel. This is really unique. So -1 to the n, as n progresses from 0 to 1 to 2 to 3, doesn't -1 to the n just go 1, -1, 1, -1, 1, -1, back and forth, back and forth? So this, it diverges because, say again? It's not decreasing. Never stops going back and forth, back and forth. Therefore, what would tell us diverging? Say again? Kind of, sort of. What's the part of the alternating series test? Nth term test. So here's what you could say. You could say the limit as n goes towards infinity of -1 to the n does not equal 0. It just goes between 1 and -1 repeatedly, but it doesn't go towards 0. Therefore, diverges, probably nth term test. And so therefore, because of that, I think my final answer would just be double open. It would be -3, open on that, open on 1. That would be my final interval of convergence. Sorry, we squeezed that one in there. I kept you a little bit late. Have a wonderful rest of your day. Good work. We'll pick this up. We'll do more of these next time, okay? Don't worry. Yeah.
Wouldn't that just be like adding up -1 and 1 though? So wouldn't that
So think about your partial sums, right? So the sigma means we're adding those up. So like if it goes 1, -1, 1, -1, wouldn't the partial sums just alternate between 0 and 1? 0, 1, 0, 1, 0, 1, 0, 1. So what's the answer if you added all those up? It's actually heading towards infinity, right? So it's going to be 0 or 1,
Okay.
right? As you head towards infinity, it's going to be 0 or 1. The point is it's not going towards 0.
Okay.
And essentially, there is no answer. Some people would say that it diverges due to oscillation,
Okay.
because it just goes back and forth, back and forth. I prefer the nth term test simply because it's like the nth term's not 0. So,
Okay.
good question. We're going kind of deep. Appreciate you.
It kind of helped like reviewing ratio tests and stuff.